So, now having understood the connectivity, the actual physical connectivity, let us come to the OSI network architecture. A typical, a very generic general purpose network, this is a very general purpose model, and in the various special networks you have some sort of an adaptation of these network architecture. In all networks adapt this generic OSI network architecture in certain ways. So, in the generic standard you have actually, when over a network, when one computer talks to the another, it need not know what is the network connectivity, what is the address. You just when one person chats with another person over a long distance, sometimes over the globe. So, it is actually a virtual communication, but actually physically these data or the text, suppose, which you are typing, has to physically travel from your network across various communication channels and physically reach the other computer, which may be thousands of miles away. So, this is achieved through a layer of protocols. Okay. Each protocol gives a service to the protocol above, so that the protocol above and hides certain unnecessary details from the protocol above. So, the protocol above always sees its own communication as across some virtual channel, and is freed from several technical details. Otherwise, it would have been absolutely impossible for us to do any communication over a network. So, the communication is actually whole system is actually organized in layers, and any message which is generated at a top layer will come down across the layers, finally reach the communication channel and the electrical communication, then it will travel across various nodes, and then finally will go up and reach the top layer of the destination process. So, typically you have physical layer, which is actually the electrical layer, where the actual electrical communication takes place, modulation communication over any medium, fiber optic, radio, wire, whatever. Data link layer is the next layer, which actually provides increases the reliability of the electrical communication. So, here the data is not it is still treated as binary data, packets are assembled, error codes are attached, so that during transmission, if some data error occurs, that can be detected. These transport and network layers actually take care of the networking problems. So, firstly it does things like routing. So, if you want to if you are sending an email message from here to Japan from your host to whom you send, where should it go? So, this kind of routing information is done by network layer. Then there are sometimes they do things like congestion control. So, some particular channels may be down, they may be choked. So, if data is not going through these channels, there are mechanisms by which people can do things like flow control. So, this network and transport layers actually take care of the network topology, loading, and network communication. So, once you have taken care of these, from the session and presentation layers, it appears as if you have this is the physical communication, this is the physical communication, digital communication, this is the network configuration and network performance ensuring. So, once you have these two layers, these layers sitting on this and this actually sees some kind of a virtual session between two computers. So, it does not know, it is completely oblivious of how, through which path in the network this particular message is going. So, it does not know, it just knows. So, it sets a session. Presentation layers are generally rudimentary, they are not very strong, and it is the application layer which is application layers are configured for typical kinds of application, like you want to have a remote terminal. So, you want your PC to actually work as a terminal to a server, which may be elsewhere on the network. So, this is a remote terminal service. There can be an email service, right. So, so these various kinds of common kinds of applications, various kinds of FTP service. So, file transfer. So, such things are the particular details of these are actually handled by the application layer, and the application layer once. So, then the application layer actually calls a session layer, and says that you please set up a session for this particular application, and then the session layer gives those its session messages to the transport and network layer, which decides how it will go, and then they actually finally puts all the addresses etc., and then finally these get to the data link layer, and then they actually are transmitted in the medium. The user layer, normally this user layer in this is OSI network layer is network architecture is actually a 7-layer protocol, which does not have the user layer, because for general purpose computing the user layer can be of enormous variety. So, therefore, the user layer is actually not specified, but as we will see that in the particular case of industrial automation networks, this is adapted, right. So, what is done is we will skip these slides and see the Fieldbus network architecture. So, in the Fieldbus network architecture there are certain differences. So, first difference is that the network in the factory is actually fixed, it does not change. Second thing is that what kind of messages, that is the loading on the network, how many messages are coming, frequency of messages arriving on the network are also more or less constant, because all the time, I mean, once it is designed it is fixed. It is not that new processes are being, I mean, large number of new processes can be suddenly generated, because we know what kind of computations are actually going on in this network. So, therefore, this what I mean to say is that the transport and network layer functionality is nearly removed. So, therefore, it is good to remove the transport and network layer. Therefore, the Fieldbus network actually does not have, actually has very rudimentary transport and network layer, right. So, so it has a physical layer, it also has the data link layer, which does also part of the little bit of, it actually puts the addresses, it actually ensures that is who will transmit when, say the medium access protocol etc., for cyclic and acyclic communication is also handled in the data link layer. And these layers 3 through 6, that means session, presentation and application are actually application is there, 3 to 5 I would say, physical, data link, network, transport and session layers. Networks, 3 through 6, networks, transport, session and presentation, these 4 layers are actually removed. Then on top of that you have an application layer, which application layer is, so you have Fieldbus application layer, which is broken into 2 sub layers. One is called the Fieldbus message sub layer, the other is called the Fieldbus access sub layer. So, using the Fieldbus access sub layer provides various kinds of addressing functionality, and the Fieldbus message sub layer actually configures the messages which are coming from the user layer. So, in contrast, the Fieldbus network proposes a major user layer, because here the computations are not of that much variety. Number one, they are largely uniform, they are all for process automation tasks, and secondly, because of the fact that it is necessary for easy configurability, it is necessary that so enormous flexibility is actually not needed. So, you can create various kinds of templates, and you can create a separate layer within which it will be easier for the application engineer, for the process engineer to actually program his application. So, therefore, an user layer is proposed. So, one layer is added and 4 layers are deleted. So, you have this is the Fieldbus protocol structure. So, you have finally the Fieldbus architecture. So, you have the physical layer, the data link layer and the application layer broken up into 2 parts, and then you have the user and user layer, which involves the function blocks, which are abstract computing blocks which specify abstract communication, let us say between an analog input device and a process controller, or a process controller and an analog output device. So, it will just abstractly describe this in terms of function blocks, and then the network communication through this, I mean among these function blocks will be automatically realized by this part of the network, right. So, so this is the Fieldbus protocol. In this lesson we will be mainly concentrating on the data link layer and the physical layer. Physical layer we have already discussed, and in the next lecture we will be talking about the user layer and the Fieldbus application layer. So, the Fieldbus, as I was telling, it defines user layer for interoperability. So, that every device, so all the Fieldbus devices have to be of a certain standard as far as software interfacing or data formats are concerned. So, those data formats have been already specified in the standard, and any Fieldbus device must comply with that standard, so that they can become immediately interoperable. And these are defined in the user layer protocols. The Fieldbus message specification, so the user layer just abstractly gives. So, maybe an analog input block simply in its user layer it simply generates a value. So, this particular temperature signal has to go to the PID controller, it says. Now, for transmitting that to the PID controller, this has to be actually made into a message, and then a message has to be configured into a packet, and then it has to be sent with after all the addressing, etc. So, the Fieldbus message specification actually builds up the message data structure for communication as per requirements, and in fact there may be several function block processes within a device. So, all these devices frequently are generating data. So, they have to be put in the form of messages and then transmitted. And then the Fieldbus access sublayer, once it gets the packet, this is to be transmitted, then the Fieldbus access sublayer adds addresses and the networking information such that this can actually reach another device on the bus. Each device has a unique address. So, and unless you, since there is a shared medium, unless you transmit your messages, unless your messages contain addresses, the devices will not be able to understand whether a particular data that it has seen, because everybody is actually listening on the same bus. People are transmitting on the same bus, and every device is actually listening on the same bus and picking up the data which is meant for it. So, the Fieldbus access sublayer provides in this way, by providing addresses, provides a virtual communication channel, so that the top layers do not need to worry about how each device is actually sensing and then picking up the data meant for it. So, it need not bother about that. The data link layer actually manages the communication protocol. It takes care of the digital communication details, error coding, parity checking, etc. And the physical layer provides the electrical and medium dependent. So, if you have wire, if you have RF, then there has to be radio transmission. If you have fiber optics, then there has to be optical communication. So, all these details are handled by the physical layers. And okay, levels 3 to 6 are dropped for efficiency. So, without going into the physical layer, because that involves a lot of electronics basically, and generally communication electronics. So, we do not want to get into that in this course. So, rather we look at the data link layer. In the data link layer, the features are that you have centralized bus mastership. This is very important to understand, because you are having a bus on which everything is hanging, right. So, if a particular device transmits on this bus, there is signal existing everywhere on this connector. So, all the other devices can get it, and it is very important that no two devices never transmit data at the same time on the medium, because then the data is going to be garbled. So, therefore, there has to be a device which will decide who will speak at what time on the bus. So, this is achieved by what is known as bus mastership. So, the bus master distributes the right to transmit among the devices depending on their needs and depending on how you have configured it. Communication can be cyclic as well as acyclic, that is, some devices will every say 1 second they will send a packet. So, they require cyclic communication. There are some maybe acyclic which will be suddenly required, maybe due to some alarm condition and things like that. So, these two kinds of communication are supported by the data link layers, and sometimes you have features for connection oriented as well as connection less data transfer. This is connection less. So, you can have broadcast where you are not giving addresses, or you can have a connection oriented that this is meant for only this node only, right. So, these are supported by the data link layer. So, pictorially it looks like this. So, on the bus, this is the field bus, there are various devices, these are basic devices, BD basic devices, and these are link masters. So, LM is a kind of device which is capable of becoming a link master, and there is among the link masters there is a particular device which is called the active link active scheduler. So, at this time this link master can also become the link active scheduler, but it is at this time idle. So, these are idle. Sometimes you provide more link masters, because if for some reason this link master fails, then who will ensure the communication. So, there are some other link masters which are always kept in hot standby, so that they can immediately take over the communication and the control and coordination will continue. This is very important, right. So, exactly same diagram, this is repeated. So, these are link masters and they are basic devices. Basic devices are not capable of becoming link masters or link active schedulers, while link masters are capable of becoming link active schedulers. So, LD is a linking device, LD interfaces H1 segments with an HSE, or I do not know what HSE means. Link master, that is what I said. BD is basic device, a device not capable of becoming a link master. So, link active scheduler is as I said, it is a bus master which distributes write to transmit to all devices. It is actually a functionality, some software which may be present in several link masters for fault tolerance, and it actually does the scheduling of the various soft and hard real time communication tasks. So, soft real time communication tasks are those which also need to be finished in time, but even if they are slightly delayed, there is not so much of a problem. But hard real time tasks are those, if you cannot finish those tasks, those computing and communication tasks in time, then the system may completely collapse, right. So, it must, so for you in your scheduling you have to take care such that the hard real time tasks are definitely finished within time. So, the link active scheduler also has to these you can always keep on, as we said, that there is easy configurability. So, you can add a device simply to the network, and the link active scheduler also has to look for whether some new device has been connected, and then has to configure them, and then have to take care of their communication needs. So, it also searches for added and removed devices. Similarly, if a device is removed, it has to take it off from its scheduling list. For cyclic communication, typically applicable in the case of control. So, transfer process variable or transfer valve position is just an example. So, it continuously has to take the process variable, compute the controls, and then output to an output device. So, this goes on, right. So, this is an example of cyclic communication. So, if there is cyclic communication, what the link active scheduler does is that it issues a CD or compel data token to a particular device. So, once the compel data token is given, this device to which this CD token was issued must respond with a data token, right, and then this it will send on the bus, and then all the devices are actually all the time looking for the data. So, the device which needs the data token will actually will receive it and will take it and then use it. For acyclic communication typically occurs when you have alert or event notifications, you have some operator data update. Sometimes you like to see some trends, so you can ask for some trend data. You can change set points, or you can give other kinds of commands to change operating modes. collect maintenance information, etc. So, these are not cyclic informations, but demand driven. Sometimes if they are invoked, then that communication has to be obtained. For this, the LAS polls each device with a PT token. PT is a pass token. So, if a device has something to communicate, it will take the pass token and then will communicate. If it doesn't have have anything to communicate, it will simply pass the token to the next device. So, whoever needs it will hold the token and then will transmit the data. And the communication is actually organized overall into cycles called macro cycles, and within each macro cycle, so macro cycle is the basic cycle over which the communication is periodic, and then within macro cycles you have elementary cycles. So, an elementary cycle is decided by the fastest, by the device which needs to communicate the fastest. So, you know, if you have, so let's see the next example, we will understand it better. So, for example, take this loop. This is a PID loop with, say, an analog input, a PID and an analog output. So, these are actually on different devices, and the analog input. So, they are all on the network, and the analog input. This is a function block representation. So, virtually this AI must communicate with PID, and then PID must communicate with AO, and they are actually physically different devices. So, in this case you see that suppose there are, so this is an example of several devices. So, suppose it can very well happen that one device needs to talk 2 times in 1 second, cyclic, both are cyclic, but another device needs to talk only once. So, you see how it is organized. So, you have a so the macro cycle is actually decided by the slowest device. So, since here the slowest device needs to talk only every 1 second. So, therefore, you have a 1 second macro cycle. On the other hand, the elementary cycles are decided by the fastest device. So, in this case the fastest device needs to talk twice in a second. So, therefore, in one macro cycle you have 2 elementary cycles. So, first time what happens is that see CD1 DT1. So, the first device talks, then CD2 DT2, the second device talks, and then some time is in this elementary cycle, some time is kept free. This time is kept for acyclic communication. So, if there is any acyclic communication requirement, then this PTN and DTN, suppose this some nth device needs to do some acyclic communication. So, this PT will be passed and this DT will be transmitted. Now, in the next macro cycle you see that because CD1 and DT1 speaks, because it needs to talk twice in a second, while CD2 and DT2 is skipped because the second device does not need to speak twice in a second, and this whole time is actually utilized for acyclic communication, and then the next 2 acyclic communication cycles go on, and in the so now this macro cycle ends and the second macro cycle begins. So, the first elementary cycle of the second macro cycle is here, in which again CD1 CD2 and CD1 DT1 and CD2 DT2 will take place. So, this is the basic way in which the communication goes on here. So, for example, see in that communication loop things are serialized also. So, first in this communication loop what happens is that first the AI 101 to PID 101 takes place. So, the analog input gives feedback to the PID controller, then the PID controller now the PID controller, as we had seen in the previous diagram, that the previous PID controller and the analog output devices were on the same physical device. So, there is no need for communication. So, this PID controller giving value to AO is there is no need for communication, but this analog output may also have to be transmitted to the host or some operator station which wants to see what kind of outputs are going to the plant. So, for that you need a communication. So, that is so at this point of time, so here the analog input process computes input samples and then a communication is scheduled. After this communication ends, the PID data has got the result, so it will compute, and then the PID will directly give, and then the AI block will compute. This does not require any communication, because the PID and the AO block are on the same physical device, no communication is required, and then the AO block will communicate on the network with the host, right. So, this is the way this PID loop computation and communication will go on. So, this brings us to the end of the lesson. So, let us review it. So, in this lesson we have seen the basic introduction and motivation of having a network. So, obviously, here I would like to make a comment that obviously there are advantages of having a network over a simple analog or point to point digital communication system, but one has to remember that the investments required for the Fieldbus network, all kinds of software, the smart Fieldbus devices, all these things, I mean the application domain must be large enough and must require enough quality and enough, that is the cost of setting up this Fieldbus network must be justified. So, even if it is quite elaborate and gives lot of functionality, but one should have need for that functionality, and using that functionality, I mean revenue should be returned. So, that is this is another comment. So, introduction and motivation, then we have seen the physical layer features, and we have seen that how these are connected, how these are to be connected, and how using repeaters and then digital communication you can have very large networks, and you can have wiring advantages, and you can have very reliable data communication. Then we have seen the network protocol architecture, and we have seen that it is basically some kind of an adaptation for the special purpose of plant wide control of the OSI layers, and we have seen what are the layers existing in the Fieldbus architecture. Then we have seen the mechanisms for arbiting communication rights among the network devices. So, how cyclic and acyclic communication goes on by, and how centralized bus masters issue tokens to particular devices which take them and then transmit data. So, this brings us to the last thing, points to ponder, some questions. So, for what kind of application is the network such as Fieldbus justified, right. So, I raised this point immediately. So, you can think of some application where this will be justified. Why are network and transport layers absent in the Fieldbus network? This also has been discussed. Which communication mode constitutes the dominant traffic, cyclic or acyclic? So, you can think of the various process automation tasks and then decide which is. Mention 2 advantages of distributed control over centralized control. So, with this I would like to conclude today. Thank you very much.